So I'll give something of an overview. What I'm going to do is I'm going to start off giving an overview of where we're coming from on this project and sort of where it sits in the larger frame of things. And then I'll turn it over to Robert. This is his thesis as we've been working on this together. So he'll talk through things. Make sure that you ask him really hard questions, because we eventually will anyway. So that said, Bootstrap. Take a minute and read through this. So what we had in the 1970s, the 1980s, in terms of computers, started to change in the 1990s as computers and the programs and the systems they ran on became more sophisticated. People started exploring the use of computers in education probably as soon as the first microprocessors came out, and especially once personal computing came out in the late 1970s, early 1980s. How many people here have heard of Seymour Papert? You're not doing a good job in your foundations class, so that's all the hands. That all we get here? Okay, so Seymour Papert. Okay, Seymour Papert is at MIT, and he has this idea of using computers to help kids construct knowledge and helping them solve problems through the use of computers. This took off in the 1980s. And so one of the things here that this author, Robertson, was lamenting here is that with the increase in the capabilities and the technical aspects of computers, we started focusing on the surface features of the technology. In some ways this was good because it allows us to do a lot more things. In other ways, we end up with things like Math Baseball and Math Blaster and things that are just basically electronic worksheets online. And coming from an instructional design standpoint, we're saying, wait a sec, we're not doing anything more than just giving a worksheet in a different format. And he was lamenting the fact that previously what had happened is they're having students work and look at some of the inner workings of programming and how computers work, and this enabled them to construct and to build things. So this may be dating myself, but what is this?
Triangle.
What's that?
A triangle.
A triangle. Okay.
Forward, left, 33. Forward, left, 33.
Okay, when I was in third grade, they told me this was a turtle.
I was drawing the shape.
And he was drawing the shape. So let's go ahead and draw a shape. I've got one of my shapes is bleaking here. This is what I did in third grade out in the computer lab that they annexed to the school because it could heat itself, and that kept it cool because I grew up in a ski town. So this is what Seymour Papert built and built a legacy on. And today, actually, a whole bunch of his what do you call them, proteges, a bunch of his students, a bunch of his advisees are actually leading a lot of areas in our field in terms of instructional design and the use of games and other things to teach. This is Logo. How many people here have heard of Logo? All right, so Logo was Seymour Papert's creation. His idea with Logo was that by programming, students were going to learn to think through things, to build things better. They were going to learn problem solving, and they were going to work on real-world problems that were meaningful to them. There were tons and tons and tons and tons of studies done on Logo. During the 1980s, this was everywhere, in schools, across the world. They probably even used it up in Canada. Did you use it up in Canada?
They did.
I mean, that's telling something right there. I didn't mean to offend anybody. By the way, Canada beats us out in most academic areas. So there's our nod to that there. But through the studies of Logo here, we see that we had increased problem solving, pattern recognition, fraction, geometry, variable, spatial, and symbolic reasoning. It goes on beyond just the cognitive benefits in geometry, the cognitive benefits in other aspects, as well as creativity. And in study after study, there were lots of positive results. There were lots of results that weren't positive and neutral results. Roy P. How many people ever heard of Roy P.? Okay, distributed cognition. He kind of hung his hat in the 1980s on criticizing what was going on with Logo and saying, it wasn't any good. So you had a lot of these things going on both sides. But a lot of good was done with the logo studies in terms of students can learn to program and they can do some of this. Eventually, though, they died out. One of the things he helped to solve with teaching students logo is some of these common problems that still persist today in terms of schooling. We see students have trouble understanding variables, they have trouble understanding functions, and perhaps one of the most consistent complaints in math education is that students don't see the purpose. How good are we going to do applying these things in the real world? Yes?
I taught a graduate level assessment course in New York, and I had a math teacher, an in-practice math teacher taking the class, and page after page of her assessments were figures and charts and calculations. And I said, well, where's the practical application? She sat back and said, I can't think of one. That was a math teacher.
That is one of the reasons why. That's exactly, and that's one of the things that we want to get at. Thank you for sharing that. That's a great anecdote. That's part of the problem, is thinking through this. So students have problems doing problems like this, solving problems like this. So I thought, are you smarter than a 10th grader? We'll do this right now. So, so let's do this really quickly. If I've got g of x equals 5x divided by 2, hey, I haven't had math since in 15 years, so so this is fair game for me to ask this of you. G of x equals 5x divided by 2. What if we've got g of x where x equals 3? What's the answer?
7.5.
You say 7.5. So walk me through how you did that.
So you replace the x as the variable with the particular number, 3. And so 5 times 3 divided by 2 is 7.5.
Great. One of the problems with showing kids this way is that previous to getting to functions in mathematics, what did g parentheses x mean? What? Times. All of a sudden we're using the same notation to ask them to do something different. This often confuses students. It confused me as a student. I was able to follow instructions and do this. Here's one that's a little more complex. If we've got f of x where x is 3, what would the solution to this be? So we've got 15. 4 times 3 is 12. Plus 3 times 6 is 18 divided by 3, 6. So, all right. What about this? What if we ask you to evaluate f of g of x? People are laughing now. This is nervous laughs. Okay. So why did you give me a nervous laugh?
Because I need paper.
Because you need paper. Hey,
I can't do that in my head.
But it's perfectly fine to use paper for this. The question, students see this and a lot of students lock up. I say, I can't do that. You confuse me with the notation, you confuse me with what it is that this even means. Even though they've been doing it for years, we've just used a y instead of f of x. Some math educators, Moses and Cobb here, one of the things that they talk about is we need more project-based approach, kind of what Jeremy was referring to back here. We need a project-based approach using a version of experiential learning where each step is designed to help students bridge the transition from real life to mathematical language and operations. In other words, give it some meaning. There are lots of ways that we've looked at in instructional technology and design and learning sciences and cognitive sciences to try and give people more meaning. We've got the situated revolution that started 20-something years ago. So the question is programming more meaningful to the students? Here's my little programmer. And he says, once I made that turtle move, I just couldn't stop programming. I really enjoyed the feeling of being able to make shapes. Okay, so honestly, I've never met a programmer who says they got their start with logo. I don't know. Jeremy, have you ever met?
Yes, me.
Okay, so there you go.
Actually, I was doing basic A before logo, but logo got me into the graphics.
Oh, okay, logo got me. I apologize. Okay, so it's Jeremy right there. Ladies and gentlemen, I present to you. Okay, so I'm not criticizing it as necessarily a bad platform, but the problem is, in many cases, it died off because people didn't see the relevance. They weren't making the connection the way that others had hoped for. And a lot of people have taken that research and tried to push it forward in more meaningful ways. We may be trying to do something like that this summer with 1st through 4th graders as well, in more tactile, hands-on ways. Jasmine Kafai is actually one of Seymour Papert's pupils. And she writes a lot and studies a lot on the use of games in education. And she talks about instructionist and constructionist approaches to games. And where we have today a lot of instructionist approaches to games that say, you know what, we can tap into students' motivation. If we have them do the same thing but in a game format. And that's what she terms this instructionist approach to gaming and to learning through the use of games. What she proposes here, she says, far fewer people have sought to turn the tables by making games for learning instead of playing games for learning. And this is an approach that we personally believed in, and we had started to experiment with some flash curriculum when we met another computer science professor here who had worked with a group who had actually already created a curriculum where students were building games to learn the mathematics and to learn the programming. So students actually have the opportunity to practice a whole lot of mathematics by making a very simple game. They wouldn't get the same opportunity if they were just playing the game. Let's take a game. I've got boys that are 9 and 7 years old, and a 2-year-old. Let me tell you, he asks to play plenty of games. He wakes up every morning and he says, iPad. So we've gone through withdrawal as we've taken that away from him. But just a basic game. This is what 90%, maybe 80-90% of the games that my kids play online at Disney.com or Cartoon Network or other Lego.com especially. 90% of the games are really the same format in terms of the game. So let's look at a basic game. Let's suppose we've got this guy, what do we call this? Biker bash or something like this. Okay, so we've got a biker, and we want to move this biker across the screen, and maybe we can add things to the game as we go. So first we have a biker. Well, if I want to move him across the screen, how might I move him across the screen? Well, right now,
touch your finger to the screen.
Touch my finger to the screen and drag him over the screen. Let's try that. Okay. Didn't work. Okay, so, but we could do that. And they could program that. They could make that work, but they still need to know something about the screen. If we were to look at this and we were to think a screen is actually just a grid. And if they understand the X and Y aspects of this grid, we might say that this guy is at position 014 right now. So all of a sudden, we're giving students a way to practice coordinate systems and an understanding of coordinate systems. So they want to move them across the screen. Maybe the student says, each time you touch the right arrow, I'm going to move this guy 2 spaces. I'm going to increase my X by 2 each time. So now they're starting to understand and practice coordinate geometry. Let's make this game a little more exciting. What if we were to give a score to this game? That's typical. We've got scores in games. And let's suppose we've got this. We've got to jump over these logs so this biker dude doesn't biff it. We've got a score up in the upper right-hand corner. We make this guy jump over this log. Congratulations, you've jumped over the log. What happens? Oh man, my score was supposed to change. I guess I messed that one up. So your score is supposed to change. Score goes up. This enables students to practice the concept of variable. They've got a variable score that increases or decreases, that changes over time. Variable has been shown to be something that students actually have a lot of trouble with. Let's make this game a little more exciting. Let's make it paintball biker bash or something like this. So we're going to throw some paintballs at this guy. So this paintball is going to collide with him, and you can see what's going to happen. No, don't do it! Oh no! Okay, so splat. Okay. So they ask your students the question, how do you know when the paintball has hit the biker? Or if.
Splattered.
What's that?
It's splattered with paint.
It's splattered with paint, but I had to tell it to splatter.
Oh.
As the programmer now. See, this isn't just playing the game. Now I have to know. Let's look at it in slow motion. Maybe that'll help. Okay, so looking at it in slow motion, I'll put this grid back on here. I already know how far this distance is because I know that it's on a grid. I also know how high up it is in this distance. What I don't know is that diagonal between the two. Well, we tell kids all the time, there's this thing called the Pythagorean theorem that's really important, and then they never see it in the rest of their lives and may end up never using it. This gives them a way to actually practice the Pythagorean theorem. So, using the distance formula, the Pythagorean theorem, how do I know when my paintball has hit my biker? What's that?
I was going to say when the coordinates equal each other.
When the coordinates equal each other. Or when this distance here
Is 0, okay.
is 0. When the distance is 0, or maybe we want to, anything within 5 or something, right? So when that is 0, we know that they've touched. In other words, we're giving students a way to use the Pythagorean theorem. In order to do all of these things in this game, they've actually done a number of different mathematical, they've practiced a number of different mathematical concepts. They've practiced coordinate systems, they'll have practiced variables, they'll have practiced using the Pythagorean theorem, they'll have practiced functions, which is notoriously difficult, and they'll have practiced order of operations in order to make all of this work. There are other things that they practice, but this is just a very basic game that we let students use. So it ended up that there was somebody who was already doing this type of stuff. And we hooked up with them and worked on the Bootstrap. So I'm going to let Robert go ahead and talk about Bootstrap and kind of what we did and what we found.
Great. Thanks. Okay, so again, how many people saw the presentation on Bootstrap a year ago? Just one, yeah. Okay, right there. Okay, great. So some of this will be new, but a lot of it will be fun. So let's come back here for just a moment. Schanzer goes out and he says, hey, this is a really great curriculum, and as these students learn how to program computer games, they're going to learn math. And one thing that Schanzer really preaches is that he wants this to be their first introduction to algebra. He wants to get them in 6th and 7th grade and show them these concepts so that as they progress through algebra, these things are going to secure, they're going to gel within these students. So, along with my thesis, I said, all right, let's see the proof in the pudding. Let's go ahead and take a look at some of these courses, and let's see if this really did happen. Now, we went through 3 different schools. Dixon Middle School, we did a pilot study, and they did an after-school program for several weeks. Vista Heights Middle School, out in Saratoga Springs, we did a full course with a full study, as well as Lehigh High School. These were students that were actually getting credit for the course as a elective.
And you'll notice as well, the Lehigh High School students were very different. They were 10th through 12th graders. They were older.
They were older.
But they weren't self-selecting.
Yeah. And they also had all completed Algebra 1, but not really anything beyond that.
And most of them, they were all recommended to be in the course, but they were all struggling students. It was very different.
Yeah, it was a very interesting course.
Courtney's not here. She was actually our teacher, one of the teachers for that course. But yeah.
Yeah.
You can ask her.
All right. So what we did is in each of these schools, okay, so we had the course set up, and then we also set up a control group. The control group consisted of students at the school, approximately the same age, approximately the same level of skills as far as math is concerned, and also not in the course. So essentially you've got your control group, and we're going to do assessments taken about the same time as the control or as the treatment group. One of the things for criteria for the control group is they had to turn in parental consent forms, as well as they had to put their names on the first and last assessment that we gave them so we could actually see which one matched up. It was amazing how many assessments we got back with no name, an original name, half done, for done anyway. So it was interesting. We had far more assessments than we needed, but we had a sufficient for both of them. And again, the schools were Dixon, Vista Heights, and Lehigh High School. All right, now let me show you what one of these games looks like. And there we go. Now, in each game, you had a character or an actor, And this particular student used an animated image, which really got a lot of fun. If you notice, there's nothing corresponding to his jumping around and smiling other than it's just kind of going around. Now, within each of these games, there was a target. And the target for this guy is the candy. How many people here are familiar with the Candy Shop War? Okay? Oh, it's a great book. How many people know Brandon Mole?
Personally?
Well, those books. Read Fablehaven. Okay, same author. And so he wrote this book, The Candy Shop War. What appears to happen is this particular student... replay. There we go. That was a lot of fun. What happened is this particular student seemed to want to do this as part of an English project. That is, he did this after the Bootstrap course was completed. And then he went ahead and based his story on, okay, the kid, he wants the great candy, the magic candy, but he's got to keep away from that crazy old lady at the candy store because she's the problem. So you had a danger. And in which case, this kid, the danger is the little old lady. Another one. I really like this guy. This was in Vista Heights. They could pick whatever background they wanted. They could pick whatever actor they wanted. And in which case, you got Homer, and any guesses on what Homer is after? Yeah. And what's the danger for Homer? Yes, the broccoli. All right, there was one young lady at the Vista Heights. I really liked this. This was really some imagination. You got the fairy, and her danger is the big toad, and she, of course, wants to access the Sprite. Now, they did all this in a programming language called Racket. How many people here have used Lisp, Scheme? Okay, Racket's another name for PLT Scheme, which is kind of down through the history, come from Lisp. And it's a functional language. The idea that Schanzer had is that you would want to use a functional language as opposed to an imperative language. Okay, how many people here have done a little bit of programming? Okay, first thing you do in programming is you create a variable, right? And you give it a value. Okay, and that goes into some bucket. It stays that. And then you can reassign that variable with something. Is there anything in mathematics that corresponds to that particular idea? How about this? Okay, so in programming you want to do a loop. You want to do something over and over and over again. So you got a counter, and as this counter comes up to a certain number, you do the same thing over and over again. Does that relate to math in any way? Similar concept? Maybe, maybe not? Okay, functional programming language is more of a theoretical idea in that you are using pure functions. Function that every time you put something in, you get the same thing out. You don't have this concept of programming variables per se, but you do have the same concept as a variable in math, which is to say, this represents something. We don't care what at this time. It can represent a whole range of things. And then other ideas would be presented later. We didn't go through recursion with these students. Instead, we just mostly stopped with the functions and understanding. Nice thing about Racket, it's kind of algebraic notation. We'll take a look at that. And it's in prefix notation. How many people here have used postfix notation or reverse Polish? That's fun stuff. Use the stack. Yeah, that's one thing my wife showed me in calculator when we got married. It had a stack. It's a really good thing. This is a simple function defined in the programming language. And what you do is you define, first of all, you have the function first. We're calling a function called square it. And in square it, you pass in a variable which we're calling x. And then inside the function, we're doing some operation. Pretend this is actually a multiplication symbol. Multiply x by x. So, if you were to call this function square it 5, you would get 25. Simply put, you call it square it 0, 0. Call it square it 100, negative pi, no, okay, so So let's go over one of the things that we're trying to bring out to these students here. Why is algebra hard? As you go through school, you think about what they taught you. You taught you a variable. And what is a variable?
Placeholder.
It's a placeholder. But what are you going to do with that variable?
Change it over time.
Okay, what's the
Solve
first?
for it.
Solve for it. This says to me, solve for x. Okay, now you come up into functions. And now, what do you solve for? Well, before, this was a process. In that, well, what is x in this situation? 4. How did you figure that out? Yeah, you use a process. You go ahead and subtract 2 from both sides, you get 4 equals x. But over here, as Peter was saying, students first of all look at this and they say, I have no idea what this means. But this is an object. This is something that you use, that you can expand over time, that you can place someplace else. It represents a concept rather than something to be solved for.
So you're saying it's like a little engine or a machine?
Exactly. Isn't that what we talk about as functions as? You plug something in, you get something out. And every time you plug the same thing in, you get the same thing out. Good point. All right, so let's go over here, the shark attack. This particular student, he says, all right, my shark, he is the actor. And he wants to keep away from the surfer dude, because the surfer dude hits the shark in the head, but the shark likes to eat Dory.
Nice.
So again, we say, how do we know if the shark has come in contact with one of the other characters? And we say the Pythagorean theorem. We just tell them, okay, a squared plus b squared, and then you can get c squared. Well, we teach them how to program that using this particular syntax. Let me go over this just a little bit, explain what we're teaching these students. We're defining a function and we're calling it distance. Right? You call it just, we can call it whatever we want, but we're just trying to say, what is the distance between these two guys? Well, you put in A, and you put in B, and you square both of those, and you do the plus. Now I said this was prefix notation. That is, you put the operator first. So you say plus this and this. Prefix, infix, yeah, doesn't matter, does it? Okay, well, we'll see. And then, of course, here it's again your operator. Square rooted, and there you get the distance. Now, after they've gone through that, we give them an assessment after the class. They've gone ahead and done this wonderful work with the Pythagorean theorem. And so we come to say, hey, below is written a function in the programming language Racket. And so we define it the same way, the prefix notation, and multiply, divide, and so forth. And you say, hey, look, in mathematical notation, this could be written exactly the same as something like that. Now, what you've learned, use the Pythagorean theorem. Find the two values and determine how far apart those were. Isn't this great? We have taught them this beautiful concept, and they're ready to go. And the most common answer on this question was? Yes. They left it blank. No, they said, I don't want to try to answer that. They said, hey, doesn't that mean f times x? I've never seen anything like this before. F times x. This was one of my favorites. This is one of the students from Lehigh High School. She says, fractions scare me. You know, and we come back over here, she says, this is much nicer with the divide 4-3. I can deal with that. Fractions? No way. And of course then they say, how do I solve for x? I mean, they immediately slip back into that mode of process. So the cognitive bridge really wasn't made like we were expecting. Now, we went ahead and interviewed several students, some at Dixon, some at Vista Heights, and some at Lehigh High School. And we went over this particular script, and we said, hey, look, you write this function, define f and x is the same thing as f of x equals x plus 5. They say, yeah, that's cool. I can deal with that, okay? And they say, okay, so what would be f of 5? And they'd say 10. What was f of 0? And I do a few negative numbers to make sure, yeah, okay, they're good. Because they've been writing stuff like that on top for the past several weeks. So they're comfortable with it. And I come around and say, define f of x plus 5, and g of y is 2 times y. And say, okay, let's determine f of g2 is 9. Let's go ahead and figure that out. This is all written again in that racket programming language. I showed you they've been nesting functions before, figuring out the distance, putting square roots inside of each other. And so they'd say, yeah, I can see that. But then you come to the next one and they would say, all right, now this is the exact same thing. F of x equals x plus 5 and g of y equals 2y. Find f of g of 2. And they'd say, freak! No way! That is too confusing. Few students can make it. A lot of them, no, sorry. That's just a little bit too hard. So really what we found is that, yes, they were gaining concepts, but notational transfer is a big problem with that. Okay, so what we did is we gave pre-assessments and post-assessments to both the control group and the treatment group. The group that took the Bootstrap class and the group that was in some other class that had nothing to do with Bootstrap. But we're the same age, same math level, going through learning. We expected them to learn things about variables, functions, transfer that knowledge to advanced algebra problems like we showed you, order of operations, PEMDAS. Everybody know what PEMDAS stands for? Okay. Yeah, please excuse my durant sound like that's exactly. Parentheses, exponents, multiply, divide, add, subtract. Okay. And then we had a few other algebra concepts kind of mixed in there, kind of as control questions, just kind of see what we learned. All right. We then took the assessments and we took the categories that we expected each question, or we took the categories for each of the questions and summed up the scores. And then on between the pre and the post tests, we took the difference between those scores. And we did some statistical analysis to see, okay, did the treatment group rise in scores better than with the control group, and was it statistically significant? One thing I got to mention is normally you have a p-value in statistics of 5%, but one thing Bonferroni showed us is that if you've got 5 different groups you're doing in the same study, then you got to go ahead and do an adjustment. So we're really looking for a confidence level of 1%. With this case, we didn't have too many trick problems, so it came out just fine. All right, this is the results we got back from the students on the questions like the one I showed you, where they're trying to transfer the knowledge from their racket programming language, their Bootstrap course, into algebra questions. Ran an ANCOVA, which is we had the coefficient of the pretest along with the difference in the difference in the scores of the assessments, the pre and post tests. And you look here, over here in Vista Heights, this is Box and Whiskers graph, and nobody here in either group did worse as far as the transfer results, as opposed to the control group. Well, definitely some were guessing, some did a little better, some did worse, so they're kind of all over the map. Something you'd like to see. But you take a look, you have the ANCOVA, and then we also did regression, again, using the pretest score as a coefficient. And then we calculated the effect size. And you look at those numbers and you say, nothing consistent. This isn't anything you're going to give to a math teacher and say, I'm going to sell this. You know, this is something, I got to get me some of that. This is really cool. No, didn't quite see it in that. Probably because they left most of those questions blank. And some of these things here are the few venturous ones that answer the questions. But then we come down to the other areas that we talked about. We gave a question like this. Arrow points to N. What is n? That's a variable. Could n represent 21? I think so. Could n represent something that got lost in the transfer?
It would be like 21 plus 3.
21 plus 3, yes. Kia knows these really well because she went through and graded probably about 80 of these. Yeah, n represent 21 plus 3. Yeah, so could it represent a plus 1? Yes? No? Yes? Yes, definitely. Why? Because it's a variable. You can put whatever you want in there. And then we gave this question. Which is larger? 2n or n plus 2? Answers?
Depends what it is.
Depends? If this were a function, which would be larger?
I'm not sure if functions have size, but the outcome would depend on what the input is.
Yeah. Actually, there's no such thing as a concept of larger. They're both linear, and the lines are going to be above one or the other depending on where they cross. So a lot of students really did struggle with this. It was interesting, some of the answers. Well, because it's multiplying, it's going to be bigger, is one of the common ones. Well, we take a look at the statistical analysis of what they came back with. Okay, at Vista Heights, we had one student that actually did worse, but everybody else seemed to do much better. And again, with the control group, we kind of saw stuff all over the map, something we expected. And so as we look at the statistical analysis in the ANCOVA, those are pretty nice numbers, as well as on the regression. And the effect size is something that you could go to a math department and say, hey, if you want to help your students understand variables, here's something that really works. So variables was definitely really well understood. Now we come to functions. We ask them, okay, function, we see in a book, what does it mean? Then we had all those transferred algebra questions mixed in there. And then we had this toothpick question. Toothpick question kind of came along like this. You've got 7 toothpicks there, and you're able to make 3 triangles. How many do you need to make 7 triangles in a row? Well, normally they would start drawing out how many it would take, and then they would count them out. How many to make 20 triangles in a row? And here, I think we had several of them draw out 20 triangles in a row. But then the key question was, write a function to figure out any number of triangles. And that was the one we graded on the functions to see if they were catching on to that. And then, of course, then we put it in. I think I did see someone actually trying to do 50 on one of this. And then, of course, some ridiculously high number, which is to say, if you figured this out, you can figure the rest out. So you come to functions, and the results were, at Vista Heights, that's really good. The effect size isn't outstanding. Effect size, usually if it's 8 or 9, that's really good. If it's a 1 or above, that's just like, wow. So 5, yeah, maybe it helped. Statistics look about fine, and we got about the same thing at Lehigh High School. So there was some knowledge, some transfer of idea of functions to them, just not into the correct syntax that we were after. On the other questions, it was kind of fun. I didn't expect the students in the bootstrap course to do much better than the students in the control group. But the statistics showed me otherwise. Over here, the effect size was nothing, which is why you really want to take a look at several statistics. But the ANCOVA and regression were great. And then over on the Lehigh High School side, everything looked pretty good.
What was being tested here?
So what was being tested there, particularly Lehigh High School, we had a question saying, what is, it shows an equal sign. What is an equal sign? What does it mean? Can it mean something else? There was also the question on balancing equations. 310 plus n equals some number. And then we said n equals this, we'll make it work. Now if we added 621 to both sides, what value of n? I hope I explained that right, because the answer should be same as before. Right. So there's that question, and then some of the toothpick questions were in there also.
There's a composition of functions on it and order of operations.
Okay, so the order of operations I took out, I didn't put that as part of the other group. The composition of functions, I think I kept in the transfer. But, and then, this, okay. This comes from Vista Heights. Let's see there. There we go. Let's plug this in. Now this particular one, the PEMDAS, by the way, the statistics were really quite interesting. There was absolutely no difference between the pre and post test between the control group and the treatment group at Vista Heights. It was just exactly the same. And meanwhile at Lehigh High School, the control group didn't know it, and the bootstrap group knew it and didn't know it any better. So it was statistically not without interesting. Now this next video, at the end of each course, we do a showcase. The idea of the showcase is to show off to parents and other interested parties what the students have done. And the students get to show off their game. And as we were doing the showcase at Vista Heights, I was able to go around and interview several students. And here's just a quick video of what some of these students were saying.
And this is a squared plus b squared equals c squared. C squared is the distance between the two. Okay, so that's c squared because that's like I have it all programmed in. That's a bunch of conditionals. So I have these just like normal. And I have WASD, which goes a little slower. Then IJKL, which makes it move farther.
Oh yeah, he learned a lot. He was on this at home, trying to work on different things, and he'd come home every day saying, "Mom, I know how to do this. I can't wait to do this."
Was being able to have it at home a big help?
Yes, a very big help.
What's more fun, math or computer program?
Computer program.
Why is that?
Didn't coach them.
Yeah, so we made this and we get to play with it and stuff and test out everything. And in math, all you do is write the equation. This, you do the same thing, but then you bring your equation to life pretty much. That's why it's funner.
So what you have here is an example of, from this course, we had a student that came back after the course was done and did another game and showed it to his English class. You have students here that were taking this home and saying, "Look, Mom, what I did." You had students here that were saying, "Hey, look, we use the arrow keys, but I was also able to put in accelerators and learn how to program that." I think the key thing that we saw here, besides some of the improvements, is these students were excited with what they were doing. They liked it. Okay.
All right, so about time to wrap up. Just, so questions were raised with this. Questions we've been asking all along is, first of all, what are the concepts that we want to make sure that are covered as we work on these things? One of the questions, our goal wasn't necessarily to make these kids into, one of our goals is to make them into better mathematicians, but as well to help give them the skill of programming, and by so doing, look at other skills that are affected by it. But one of the things that we have to ask is, do we need to make those connections explicit, to where they weren't able to see that what they were doing in a programming language was the same as what they were doing algebraically in a mathematical language, where they weren't able to make those connections, or often they shut down. They just think, "Can I go back to programming?" When Robert was doing some of these interviews, we were asking that question: do the connections need to be explicit? And so we need to look at some of those. We need to make sure that prolonged engagement, honestly, they didn't really have a long enough time where they were meeting perhaps once or twice a week for 6 weeks. For an hour isn't necessarily a lot of time with the programming. The question is over time, do these things change? And then the last thing, this is kind of where we're headed with one of the projects we would like to take on. So if anybody's interested, you can talk to me afterwards. Courtney, once she comes back from maternity leave, she's going to help me work on this. There's a new Common Core in the state of Utah. And Utah has adopted the Common Core, which is common standards that are across that have been adopted by 46 states? Something like that. Most states have adopted Common Core. And so basically they say, hey, these are the standards across the board. This will enable them to share resources across states because formerly a lot of states haven't been able to do that because your state standards might not be the same as my state standards. One of the things that we would like to do is we would like to take the Common Core curriculum, which now instead of in the state of Utah, the way that secondary math, it's not going to be Algebra 1, Algebra 2, Geometry, Calculus, Trigonometry. What they're going to do is they're going to say, these are the concepts we want you to focus on, and you're going to get more of an integrated approach. Geometry, the concepts in geometry that make sense to learn at the same time as some Algebra 1 concepts. And so there are several standards. You can go to uen.org and look at this. And what we want to do is we want to find other types of games and other uses of mathematics in the creation of games that would enable students to practice these mathematics. As that, I think he was a 7th grader that through interviewing in that. As he said, well, it's more fun because here we also do the equations, but they come to life when we program. Hopefully we can enable people to have these things come to life a little bit more and enable them to practice them, see some of the practicality. Perhaps the good old tank game. I'm dating myself again here. The tank game where you've got a guy up on one ridge with the tank and a guy on another ridge, and you love firing. You love it. Well, what's the mathematics in that game? What are we using? We may be using sine curves. We may be using trigonometry in this game. And here we tell kids the quadratic formula is really important, right? And they say, no, I don't think so. I don't get this, and I don't know, maybe it's different, and I shouldn't be. We've got our math ed folks in here who can come and rip me apart afterwards. But a lot of kids say, well, how am I going to use this? We actually see a lot of these things, and we use a lot of them, and society has used them to progress throughout the centuries. And that's why they're important discoveries and uses of these things. Well, now through helping kids to create games, we can give them an opportunity to use and practice a lot of these skills. Hopefully, becoming good at both programming and becoming better at mathematics at the same time. So, thank you.